All right, AP Chemistry. We're continuing the video for the solutions to the acid-base problems. There was some technical issue. I hope it doesn't persist. So I'm going to go ahead and pick up. I've already written out the solutions to exercise 2, so let's go ahead and do that. First of all, point I was making is that this is a more common way to write acetic acid, and you're going to see it a lot more, see acetic acid quite a few times. COOH is called a carboxyl group, and so if you ask the question, why do they put 3 of the H's here and 1 of them here? That's because this is the one that's going to break off. It's always a hydrogen that's either attached to an oxygen or a nitrogen. These hydrogens are attached to a carbon. They won't break off to become acids. Why that is, you don't need to understand it. Just understand how to recognize it when you see it. So this hydrogen is going to break off to join the water. It's lost a positive charge because remember it left its electron behind with the acetic acid. It now becomes an acetate ion. So it doesn't have the H and it has the minus sign because of the extra electron. And then that proton jumped over to H2O to become hydronium H3O. Okay, let's proceed. Here you start with an ammonium ion. A neutral molecule would be ammonia, which is NH3, but this has that extra proton already attached to it. So it's going to pass it over to water. Then the NH4 becomes a neutral ammonia molecule. There's no plus or minus sign there. It's lost that proton. And that proton joined the water molecule to become H3O with a plus sign because it wasn't an entire hydrogen atom. It was just the proton from a hydrogen atom. Now they are saying to write these omitting water, but I always like to write them with water. Down at the bottom, it's a little bit jumbled, but I think you can make it out, are the solutions without water if you want to see what that looks like. Okay, finally is this particular acid. It has an extra proton that it can easily give away. You'll notice these hydrogens are attached to a nitrogen. So these could be removed to become acids, to make this an acid. These 5 hydrogens here are attached to the carbons. They're not going to ionize and become the hydronium ions. Okay, so it's going to be either attached to an oxygen or a nitrogen. So one of these protons leaves its electron behind and jumps onto the water. Notice this no longer has a charge because it has that extra electron to turn that into a neutral molecule. And then that proton jumped onto the water molecule to become H3O plus, hydronium ion. Okay, finally, this one's a little bit involved. So you'll look at this. A hydrated molecule is one that has water attached to it. So here you have aluminum, just good old aluminum by itself, but then you attach 6 water molecules to it, and that's called a hydrated water molecule. In fact, you would call this aluminum hexahydrate because it has 6 waters. Hexa means 6, hydrate means it has a water molecule attached to it. Okay, so let's look at this. We're going to take this, we're going to add it to water. The water is going to turn into a hydronium. Now what happens to this is just a little bit more involved, so I'm going to write it out down here. The reason I wrote this like this, instead of writing H2O6, I wrote H2O5 and then another H2O is because this one's going to break up here in just a minute. So if we come down here and this gives up one of its hydrogens, then down here you see exactly the same thing except it lost a hydrogen and became a hydroxide, an OH minus. This water molecule losing a proton becomes a hydroxide with a minus sign. However, it doesn't make sense to have a minus sign here and a 3 plus here. They're going to offset each other, at least one of them is. So then you come down here and it just becomes OH without the minus sign, and then the 3 reduces down to 2 plus. So this 3 plus along with this minus sign becomes 2 plus. And that's the way you would write that, that final compound right there. Okay, so now we're on to exercise 3, and it says using table 14.2. So we could go back to the previous page, and this is table 14.2. Let's talk about what it shows you. It shows you various acids. Some are strong, some are weak, and I'll zoom down just a little closer. And over here are the acid dissociation constants, basically the equilibrium constants for acid. What you need to understand is that the higher the number, And a 10 to the negative 2 is a bigger number than a 10 to the minus 10. So the bigger numbers are on top. So this is in order. So the larger K is, and it says it here in small print, but it's a stronger acid. So the larger the K, because that means more of the acid is dissociated. Remember what the equilibrium constant is. It's the products over the reactants. So as the products get bigger, that is, more of the acid breaks apart, then the K value gets bigger. So larger K is a stronger acid. Okay. There's a second principle to remember, is that the stronger the acid, now that you know how to tell which one is the stronger, has a weaker, have weaker conjugate bases. Let's just chart out why that is right here. If we take HCl and put it into water, and in this case I'm not going to write the water, it looks like this. HCl is a strong acid. A strong acid means it totally dissociates. 100% of these molecules will break apart into this. With weak acids, that's not true. So think about it. This is the strong acid, this is the acid, and this is the conjugate base. In other words, since it has a negative charge, it can accept a proton. In theory, it could accept a proton or a hydronium ion back to it. Again, proton, hydronium ion are the same thing. But think about it. If this chlorine and this hydrogen totally dissociate, they totally break apart in water, this guy would never want to take a hydrogen back, a hydronium back. Why would that happen? They're totally dissociated, so this one never acts as a base. In other words, because it never wants to take this back. Therefore, the stronger the acid, the weaker the conjugate base. So strong acids all have extremely weak conjugate bases, actually to the point that you would say, even though this is technically a conjugate base, it never acts as a base virtually. It never takes back a hydronium ion. Okay, otherwise, it wouldn't have separated from all of them in the first place. Okay, so knowing those two rules, let's go over to the next page. And it says, using that table we were just looking at, arrange the following in order their strength to the bases. You can see you have the answer down here, but let's reason out why. That's often what the AP exam will do, by the way, is it will give you an answer and then say, well, why is this? What's the reason for this? Okay, so first, we look for the conjugate bases of each of these acids. So for HCl, it would be Cl minus. For HBr, it would be Br minus. For HI, it would be I minus. These are the conjugate bases of these strong acids. For these strong acids over here, it would be ClO4 minus. Here, it would be H. You still have one H left because it's diprotic, meaning two hydrogens. So you still have HSO4, but it has lost a proton, so it's also minus. And for this one, it's NO3 minus. So if you see any of these, you know it's going to be a very, very, very weak conjugate base. So if we look up here, we do see one and only one of these conjugate bases here. Let me draw a line so this is like that. Okay. So you only see, the only one you see is Cl minus is right there. So that's going to be the weakest. It's said to arrange the following species from according to their strength as basis. So the weakest is Cl minus. Okay. The rest of them, therefore, NO2, again, that's not the same as NO3. That's different. Cn, you don't see that in the conjugate bases, and F, you don't see that. So these are all the conjugate bases of weak acids, and then we'll deal with water in a second. So what you're going to do is order those, okay? So whichever one is the strongest acid has the weakest conjugate base of these three. Let's go over to the previous page, page 6, and here we see hydrofluoric acid, here we see nitric acid, and here we see hydrocyanic acid right there. So which one is the strongest? Well, they're in order of strength of acid. So hydrofluoric is the strongest acid of those three. So that means it has the weakest conjugate base. In other words, if it wants to give away the proton, then that by logical extension means it doesn't want to take it back. Okay, so hydrofluoric is the strongest of these three weak acids. Therefore, it has the weakest conjugate base. So we're going to come over here and we're going to put it here, F minus. The next one is nitric or nitrous acid. Excuse me, nitric is actually a strong acid. Nitrous acid is the next. So it's weaker. That means it has a stronger conjugate base. And finally, the CN minus is the strongest conjugate base. Okay, let's get on screen there. Sorry about that. So in order, so strongest acid, weakest conjugate base. Next strongest acid, next weakest, just of these three. Next weakest conjugate base, and the weakest acid has the strongest conjugate base. It's just like an inverse relationship. Now, where does water fit in? Well, you have to read the notes back here, a couple of pages. And there's a little note down here. Don't skip over these. Read these as thoroughly as you can and read them several times. The strength of a conjugate base compared with that of water. So the conjugate base is much weaker. If it's a strong acid, the conjugate base is weaker than water. If it's a weak acid, the conjugate base, that's the A minus, is stronger than water. So that means we're going to put water in between. The only strong acid we had was this. That's the conjugate base of the only strong acid, HCl. So that means water is going to go in between these two. Okay, and that is the order of the conjugate bases. Okay, and there that's confirmed over there. Okay, let's move on. Okay, now that now we're going to get into, for the next several exercises, a variety of calculations of hydronium concentration, hydroxide concentration, as well as pH and K values. So what I'm going to do is I'm going to stop this video now, pick it up on the next video. So that'll be the third video. This is already the second one. And I'm going to make a table for you. It's kind of, I call it the roadmap, the acid-base roadmap, and hopefully that'll help you navigate these types of problems by telling you how to get from one variable to the other. So I will have that posted online, and I will give that to you in class. Okay, so we'll see you in class, and you can pick up with these solutions on the next video.